This is the Unit 11 Equilibrium Review. So question 1 from the review packet is, given the equation representing a closed system, which statement describes this system at equilibrium? So it is telling us that we're at equilibrium. And in order to answer it, we want to know what are the two things. There's two things that must be true for a system at equilibrium. And the first one is that the forward reaction and the reverse reaction rates must be equal. Okay, equilibrium means forward and reverse reaction rates are equal. Second thing that equilibrium means is that the concentrations of reactants and products must be constant. So we have equal forward and reverse reaction rate, and we have constant concentrations. Okay, so if I look at my first choice here, the volume of NO2 is greater than the volume of N2O4. We have no way of knowing that, and it definitely doesn't mean we don't need that for equilibrium. Second one, the volume of NO2 is less than the volume of N2O4. Once again, we don't need that for equilibrium. We don't know that. Choice 3 says the rate of the forward reaction and the rate of the reverse reaction. Rate of forward, rate of reverse are equal. And that is part of our definition of equilibrium. Forward and reverse reaction rates are equal. Choice number 3 is correct. Question 2. When a chemical reaction is at equilibrium, the concentration of each reactant and the concentration of each product must be. All right, so we just said this in the last question, right? Concentration, reactant, concentration, product, not equal. Don't jump to that conclusion. Remember, equilibrium doesn't mean everything is equal. Concentrations must be constant, unchanging. At equilibrium, the concentrations remain unchanged. Question 3. Some solid potassium nitrate remains at the bottom of a stoppered flask containing a saturated potassium nitrate solution at 22 Celsius. Which statement explains why the contents of the flask are at equilibrium? Okay, so we know that it's some solid remaining at the bottom of the saturated solution. That means that we are at an equilibrium state, saturated solutions. Which statement explains why it's at equilibrium? Well, remember that what happens here is that the KNO3 solid is in a reversible reaction with the dissolving KNO3 aqueous. And so that means that one reaction would be forward, which would be dissolving, but the opposite would be reverse, which would be recrystallization. And if we're at equilibrium, the dissolving rate must be equal to the recrystallization rate. That's forward and reverse rate. And if I look at choice number 1, the rate of the dissolving is equal to the rate of crystallization. And that is solution equilibrium. Question 4. A solution that is at equilibrium, here we go, made that a little bigger. A solution that is at equilibrium. Okay, so this right here, folks, if we see equilibrium and we see solution, that means that we are talking about a saturated solution, okay? Solutions at equilibrium must be saturated. That's the only way that the recrystallization rate is equal to the dissolving rate. Which I would like to take a second to point out is what we learned when we looked at this table right here, table G. Every one of these lines is a line of saturation, and so you can look at the line to determine where equilibrium occurs, because these are lines of saturation, and saturated solutions are at equilibrium. Question 5. Given the equilibrium at 101.3 kilopascals, that is standard pressure, right? Standard pressure. I have liquid water in a equilibrium with gaseous water. At what temperature does this equilibrium occur? All right, well, I know that water's freezing point and boiling point is at 0 degrees Celsius. I know that water's boiling point and condensing point is at 100 degrees Celsius. But I'm not going to pick choice number 1 because that is not 100 Celsius. That is 100 Kelvin. But that's okay. I can solve for this. I know that Kelvin is equal to Celsius plus 273. I have that on table T in my reference tables, which means that Kelvin is equal to the boiling point. This is the phase change, right? 100 degrees is liquid gas plus 273. And so if I'm at equilibrium here, then I must be 373. That would be the correct temperature, the boiling and condensing point of water in Kelvin. Question 6. Which type of equilibrium exists in a sealed flask containing liquid bromine and gaseous bromine at 298 Kelvin and 1 atmosphere? So this is room temperature, and this is standard pressure. Okay, so nothing that we have to really be concerned with there. What we do have to understand is that we're talking about liquid in a reversible reaction with a gas. And those are phases, and that means it would be phase equilibrium. The word static means that there's nothing moving. We don't want static. We want dynamic. Dynamic means moving back and forth, right? Forward and reverse reaction rate. And this would be an example of phase, dynamic phase equilibrium. Question 7. Given the reaction at equilibrium, which change will not affect the equilibrium concentrations of A, B, and A2B3? Well, if we are at equilibrium, there is one thing that we can add to the system that actually does not change equilibrium in any way, and that is a catalyst. Remember what a catalyst does. A catalyst lowers activation energy for both the forward and the reverse. And what that means is that adding a catalyst speeds the reaction in both directions, and there is no effect on equilibrium. So catalyst would have no effect. Question 8. Given the equation representing a system at equilibrium, which change causes equilibrium to shift? Okay, let's see. The first says increasing pressure. Now, I'd like to point out, everybody, that I have a solid, aqueous, and aqueous. And pressures only affect gases. And so I know pressure actually has no effect here. So I'm going to cross it off. Number 2 says increasing temperature. Now, the temperature is going to be related to the energy right there. So that actually probably could have a change. Let's look at the other choices here. Adding a noble gas. Well, that's just a nonsense choice. If I add a gas to the system, this is dissolving. This is a physical dissolving in water. Adding a gas has nothing to do with it. It won't do anything. Adding a catalyst, as we just saw, does not change equilibrium in any way. So my answer is definitely choice number 2, increasing temperature. Now, what does that do? If I increase temperature, that's a stress. And I must relieve the stress by getting rid of the extra heat, which would result in a shift away from the stress to the right. And that is a shift in equilibrium. So increasing temperature is the answer. Question 9. Given the equation representing a reaction at equilibrium, what occurs when the concentration of H2 is increased? Okay, so remember, Le Chatelier's principle, stress, right? Shift. Then concentration change. Okay, so we already know what the stress is. H2 is increased. So this guy right here is going to increase. Now, Le Chatelier's principle says that I must shift equilibrium to relieve the stress. I have to therefore get rid of the hydrogen. The way I would do that would be by shifting the hydrogen to the other side of the equation. Let me get it out of there. If I shift to the right, the hydrogen gets turned into ammonia. So I know what my shift is. Number 1, stress. Number 2, shift. Number 3 is concentration. And what's going to happen here? Well, whichever direction my arrow points, I'm going to get more. So I'm going to have more ammonia. But I'm going to have less of my hydrogen, and I'm going to have less of my nitrogen. Now I know my stress, my shift, and my concentration changes. Now let's look at the choices. Equilibrium shifts to the left. No and no. Equilibrium shifts to the right. Yes. The concentration of nitrogen, N2, you see right here, if I'm shifting to the right, that means that N2 decreases. Choice number 3. Equilibrium shifts right, nitrogen decreases. Oops. There we go. Question 10. Given the system at equilibrium, which change occurs when oxygen gas is added to the system? Okay, so I have to look at my stress, which is O2 added. All right, now O2 is right here. So I'm adding O2. Then I have to figure out my shift. I'm going to shift to get rid of the extra oxygen. So I'm going to push it to the other side. And that means I'm going to shift left. Okay, left. Oof. There, shift left. Okay, and then finally, what's going to happen to my concentrations? Well, the questions are all pointing to the phosphorus chloride, which, let's see here. This whole side is going to go down. Oops. Try that again. This whole side is going to go down. This whole side is going to go up. Okay, so let's take a look at which one of these makes sense. Equilibrium shifts to the right. Nope. We already said it's shifting to the left. Equilibrium shifts to the left. Yes. Concentration of PCl3. That's this right here. That's going down. I shifted away from that. Decreasing. So I know that the correct answer is number 4. Equilibrium shifts left. Concentration of phosphorus chloride decreases. Question 11. Given the reaction at equilibrium, which change will result in a decrease in nitrogen monoxide? Okay, so now this is a little different because normally we say stress, shift, concentration change. But this one is telling us the third part first. Nitrogen monoxide must decrease. Okay, so let's go backwards. How do we get it to decrease? Well, if I'm going to have less of it, that means I'm going to have to shift to the other side, right? I'm going to have to go this way. So that means my shift is going to have to be left. Okay, so how can I get it to shift left? Well, that's where these questions come in. Let's see, decreasing pressure. All right, so pressure means I have to count particles. 1 here, 2 here. Well, would you look at that? 2 total particles versus 2 total particles. That means pressure is actually not going to do anything because the particle number is the same. So they are gases, but equal particle number means pressure won't have an effect. Okay, decreasing the N2. If I decrease N2, the stress is the removal of it, and I have to get it back, and that will cause a shift towards the nitrogen. And that's what I'm looking for, a shift to the left. So choice 2 looks like it's the correct answer. Let's just double check here. Number 3 says increasing oxygen. If I increase the oxygen, that would cause a shift away from it to get rid of it. That's not what I want. And the last one says increasing temperature, which again, if I increase temperature, that would shift away to get rid of it, and that's not what I want. So yes, choice number 2. Decrease the nitrogen, and you shift left in order to get the nitrogen back. So the stress was the decreasing of the nitrogen. Choice number 2. Question 12. Given the reaction at equilibrium, if the pressure on the system is increased, the concentration of chlorine will. Okay, so we have to figure out how pressure is going to affect the system. That means we have to look at our particle number. 4, 1, for a total of 5. 2, 2, for a total of 4. I should mention, too, not be careless here, do we have gases? Yes. Pressure will have an effect because they're all gases, right? So just don't forget you got to have gaseous substances. All right. So I know that I'm going to have less pressure on my 4 side than I would on my 5 side. Pressure is increased. I have to get rid of the pressure. I have to go somewhere else. So if I'm going to get rid of the pressure, I'm going to shift to the side with 4 particles, which means that these substances increase in concentration and these substances decrease in concentration. So what's happening to chlorine? I'm shifting towards the side with fewer particles, and that is the side that is increasing. Therefore, chlorine will chlorine will increase in concentration. Increase. There we go. Okay, short answer questions here. The reaction below represents an equilibrium system of sulfur dioxide gas, oxygen gas, sulfur trioxide gas. The reaction can be catalyzed by vanadium or platinum. Okay? Compare the rate of the forward and reverse reactions at equilibrium. That's all I had to do was see the word equilibrium to tell me that the forward and reverse reaction rates are equal. That is a necessary condition of equilibrium. Okay, next question. State how equilibrium shifts when SO3 is removed from the system. So that means the SO3 has been decreased, right? I removed it. I'm going to have to shift to get it back, which is that way, to the right, which means that everything over here goes up in concentration, everything over here goes down in concentration. Okay, let's make sure we answer the question before we get ahead of ourselves here. State how equilibrium shifts. Shifts to right. Shifts to the right. Okay, last set of questions here. Taking up a lot of space, so it's hard to read the small text here. It says that in the laboratory, a 0.100 mole colorless hydrogen iodide gas is at room temperature, placed in a 1-liter flask. The flask is sealed and warmed, causing the hydrogen iodide to start decomposing. Into hydrogen iodide. During the reaction, the contents of the flask change to a pale purple color mixture of hydrogen iodide, hydrogen, and iodine gas. When the color of the mixture in the flask stops changing, the concentration of iodine is determined to be 0.013 mole per liter. The relationship between the concentration and time for the reactant and products is shown in the graph below. Okay, so this graph right here is showing us the reactants and the products. And starting here at time 0, time 1, and time 2. Okay, you have those on your paper. They didn't make their way over here to this, so I just drew them in there. First question says, state evidence from the graph that demonstrates the system is not at equilibrium between time 0 and time 1. Okay, so 0 and 1 is this time right here, right? That's 0 and 1. Why is the system not at equilibrium there? Evidence? Well, look what's happening to the concentration of the reactant. It's going down. The product is going up. So concentrations are changing. Okay? Can't have concentrations changing and be at equilibrium. They have to be constant. Okay? Well, second question says, state evidence from the graph that demonstrates that the system is at equilibrium between points time 1 and time 2. That would be right here, right? So now, why is this representing an equilibrium? Look at my concentrations. Unchanging. Unchanging. Concentrations. Concentrations are constant. Or unchanging. Okay. Let's clean this up a little bit here. All right. Number 3. Identify the substance represented by both lines A and B. So once again, I'm sorry, this is on your worksheet, but it got eliminated from here. A and B, those were the lines. Okay, so what substance is A? A is the reactant, and I'd have to come up back here to my passage. The flask is sealed and warmed, causing hydrogen iodide to decompose. That means that my reaction, or my reactant, is the hydrogen iodide, right? So A is hydrogen iodide, which is undergoing a reversible reaction, decomposing into hydrogen and iodine, like that, which means that these guys are my products, right? So that's the hydrogen iodide, and letter B is the iodine, I2, and hydrogen, H2. Okay. All right. Number 4. Compare the rate. Clean this up. Compare the rate of the forward reaction to the rate of the reverse reaction between 0 and 1. So we're back to times 0 and 1. Okay, this is a little trickier. This is right when the reaction begins. So if you look at times 0, it begins with no product, 0 product, and all reactant. That means that the reaction is only going, or at least initially, only going in the forward reaction from reactant to product, right? So between times 0 and 1, the forward is faster, right? Look at all of the product I'm making, and look at all the reactant I'm losing. So during times 0 to 1, forward reaction's going, right? But then, and we'll read the next question here, compare the rate of the forward reaction to the rate of the reverse reaction between times 1 and 2, then look what happens. Okay, we've gotten back to the equilibrium where the forward and reverse are equal because nothing is changing. Okay, so the forward and the reverse between times 1 and 2 are equal. And again, that is equilibrium.